Okay, this is the video on vector applications, and it goes along with the vector applications packet. So you should have this paper in front of you to be able to take these notes. So you should not have to write all this information down. But this gives you some information on solving word problems. Vector word problems are usually in the form of two or more forces applied to an object. Okay, so the question has to do with the magnitude and direction and the addition of vectors, which results in a resultant. So usually what you can do is you can write them as a component vector. So you would write the first force as force sub 1 cosine of the direction angle sub 1. Okay, and then the second part of the component would be force 1. Sorry, I wrote a 2. Force sub 1 sine theta. Now you could write that as a linear combination using i's and j's, but basically that's what that looks like. And a force, if you'll notice, was in the magnitude position. So force 2 then, of course, would be force sub 2 cosine of theta sine theta. When you find the magnitude of the resultant, remember that you're using the Pythagorean theorem and also the distance formula, which is basically the same thing. The direction vector, or the direction angle, is found by using the inverse tangent. And then you need to make a sketch. Obviously, make a sketch. Okay, so this is part of your packet, and so we're going to fill in some information on your packet. The velocity of a moving object is a vector because it has both magnitude and direction. The magnitude of the velocity is called the speed. A DC-10 jet aircraft is flying on a bearing of 65 degrees at 500 miles per hour. So you want to draw what this looks like. You want to do a little sketch. 65 degrees is a bearing from the north, right? So it's going to be this way. And so this angle right here is 65 degrees. It's going 500 miles per hour. Find the component form of the velocity of the airplane. Draw a diagram showing the situation. So here we go. We have this bearing of 65 degrees at 500 miles per hour. And so we know that the magnitude of the vector is 500. It's the speed, right? Miles per hour. And we know that the direction vector, be careful, the direction vector comes from the x-axis, counterclockwise. So it is actually 25 degrees. So when we go to write the component, we have 500 cosine of 25 degrees, 500 sine of 25 degrees, and then when you work that out on your calculator, you have 453. Make sure you're in degree mode. And then you have 211.31. Find the component form of the velocity. So we have force and we have direction, force and direction in the form of wind. Okay, a pilot leaves San Francisco International Airport flying due east. There's a 65 mile per hour wind with a bearing of 60. Find the compass heading the pilot should follow and determine what the plane's ground speed will be, assuming its speed with no wind is 450 miles an hour. Okay, so the diagram for this is going to look like, and it's going to be kind of important that we get this right. So this is, of course, the y-axis, the origin. I'm going to call the origin point A. And then the wind is a 65 mile an hour wind with a bearing of 60 degrees. So bearing is from the north. This is the north. So I have this wind, and this is 60-degree bearing, and it's 65 miles per hour. Okay, so the resultant is, I want the plane to fly due east. So the resultant is going to be this due east vector. So I know what its direction is, but I don't know its magnitude. I don't know how fast she'll be going at that direction or not, because the actual plane, and I guess I'm calling the plane a she, is going this direction, right? If it has to have a resultant that's in the middle, the resultant will be between the two vectors. So this, I don't know what the direction is, but I know that it's going 450 miles per hour. Okay, so that's really important, and this is kind of long, but this is really important that we understand kind of what the picture is looking like. So somewhere in here, and I don't like how long this is, so I know it's not to scale, but I just want it to be a little better. Okay, so like if I put the wind in here, this should match up, right? So let me erase this. Okay, so let's talk about this. We're going to make this point right here is going to be B, and that's the length of the vector. AB will be the length of the plane, where she needs to head to nullify the effect of the wind. The resultant is going to be D, and then this wind vector is going to be C. So I have three vectors here. And what I need to find is the magnitude of vector AD, right? And then I also need to find theta, as well as the heading or the bearing from north. So that's where we're headed. All right, so the wind is going to be vector AC. And the wind is going to be 65 miles per hour, the cosine of, and then I need this direction vector. The direction vector is going to be, the direction for that vector is 30 degrees. So 30 degrees, 65 sine 30. Okay, the plane is actually flying AB. That's where its actual heading is, plane AB. And so this is going 450 miles per hour, but I don't know what the direction vector is. I don't know what the direction angle is, sorry. I don't know why I keep saying that. Sine theta. Okay, so AD, vector AD, the resultant, is of course the sum of the wind plus the airplane. Okay, and then that is, of course, add those two vectors together. I hope I have enough room here. It would be 65 cosine of 30 plus 450 cosine of theta. And this is 65 sine of 30 plus 450 sine of theta. All right, so that's AD. All right, another way to think of AD is, since it's going due east, AD actually has a direction, right? It's 0 degrees. It has a direction angle. So it would be, this would be equal to the magnitude of AD, whatever that is, okay, which is what we're trying to find, times cosine of 0, sine of 0. Okay, the cosine of 0 is 1, the sine of 0 is 0. So basically, we know that the sine coordinate, the second component, is equal to 0. So that means that this second component, since these are both AD vectors, they're equal to 0. So I would have 65 sine 30 plus 450 sine of theta is equal to 0. So I would end up, when I subtract the 65 and divide by 450, the sine theta would be 65 sine of 30, negative, right, because I'm subtracting, divided by 450. And so that's going to equal, sine theta is going to equal negative 0.7222. If I do that in my calculator, that's what I'm going to get. And then theta, second theta, would be negative 4.14 degrees. So that's what I have found here is negative 4.14 degrees. So I don't need that, I need the bearing. So the bearing would be 90 plus 4.14. So the bearing will be 94.14 degrees. Okay, one last thing is now I have to find the magnitude of the vector. Okay, well the second component of the vector that I'm drawing is going to be 0. So really I just need to find the magnitude of vector AD, right, is just going to be the first component squared. So it's going to be 65 cosine 30 plus 450 cosine of theta, which is negative 4.14. Okay, and that, if you do all of that, the square root of all of that squared plus 0 squared, right? So is going to be just 65 cosine 30 da 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 da, which is approximately 505.12 miles per hour. And so that is how that particular problem is kind of long, but it's not difficult as long as you kind of keep things straight. Okay, now we got fish swimming downstream and upstream. And so the most important thing about this problem is that we need a picture. So that's the first thing we're going to do. So it says during one part of its migration, a salmon is swimming at 6 miles per hour and the current is flowing downstream. Okay, so I've got this salmon, it's going this way somewhere, and it's going 6 miles per hour. This is my salmon. Okay, it says that the current is flowing. This is what it would do if it was going in still water. All right, but then I've got this. Okay, this piece right here is the current that's flowing at 3 miles per hour at an angle of 7 degrees. And it means the angle to the salmon. So the angle here, this is 7 degrees. So this right here, if this is the x-axis, is negative 83 degrees. Because notice that it's from the x-axis to that. And since it's going in the counterclock or in the clockwise position, it'll be negative. Okay, so what we want to do here is I'm going to put some letters on here. This is C. This place where those two vectors come together is B, and then this is A. So what I want to do is I need to find the length or the magnitude that the salmon is swimming against the current. So this is the one I need to find. Salmon against current. So I need to find the magnitude of that vector. So I need CB, I know, is going to be the resultant of the salmon. Sorry, I've got the salmon going backwards. It's going this direction. CA plus AB, vector AB. Okay, so that's what I have. I know that the CA vector, if I write the component form, will be 0, 6. Okay, and then I know that the AB vector is going to be 3 cosine of negative 83 degrees, 3 sine of negative 83 degrees. So the CB vector is going to be those two added together. So I've got 0 plus 3 cosine of negative 83, and 6 plus 3 sine of negative 83 degrees. And that is approximately 0.37 and 3.02. So the speed is the magnitude of 0.37 squared plus 3.02 squared, which is approximately 3.04 miles per hour upstream. And that is how that one goes. Okay, one last problem. This is the Pudge problem. I really like this one. It's just a silly one, but it has to do with forces above and below the x-axis. And so what you have here is you have two children that are walking a dog named Pudge. And he's very strong and stubborn, and so it takes 2 leashes and 2 children. All right. So it says the children are pulling on the dog with forces of 27 and 23 pounds at angles of 18 above the horizontal and 15 below. And we want to know how hard is Pudge pulling if the dog holds the children at a standstill. So they're playing tug of war. So I have the horizontal. I'm going to draw the horizontal here. And I've got 2 leashes. I've got 1 leash. This is Pudge over here. I've got 1 leash that's 23 pounds of magnitude of force, right? That is 18 above the horizontal. And then I have another leash, slightly longer, 27 pounds, and it is 15 degrees below the horizontal. All right? And so what we want to know is how hard is the dog pulling against those 2 forces. So I'm going to write each one as a component vector. So the blue would be 23 cosine of 18 degrees and 23 sine of 18 degrees. Okay, so that's the blue child. And then the red child will be 27 cosine of 15 degrees, 27 sine of 15 degrees. Okay? And then what you want to do is add the 2 vectors together, and you get 47 degrees, 0.954, and 0.11928. I didn't round very much. And then you want to just find the magnitude of this vector. So we'll take 47.954 and square it, and we'll take 0.11928 and square it, and you're going to get approximately 47.95 pounds.